Hello, this podcast is on horizontally launched projectiles. First, we're going to take a look at projectile motion in general and go over the basic concepts. Then we're going to get into the special case of horizontal projectiles. We're going to review how to analyze freefall problems, and lastly, learn how to analyze horizontal projectile motion. So the basic concepts of projectile motion: the projectile travels vertically and horizontally at the same time, which creates a parabolic path, as we can see here in the lower right. The only forces acting on the projectile once it's launched are gravity and air resistance. The gravity force is always going to be acting in the down direction. However, the air resistance is always going to change, so it's opposing the direction of motion. Now, we're going to ignore air resistance because it complicates the math too much. Some examples of projectile motion are throwing or kicking a ball, shooting a rifle, jumping, and diving, and there's plenty of others. We must look at each dimension separately. Vertically, forces, we only have gravity. Motion, free fall, also known as uniform acceleration. And it's important to know that the height and initial vertical velocity determine how long the projectile is in the air. Horizontally, there are no forces acting on it since we're ignoring air resistance. The motion is constant velocity. The initial horizontal velocity and the time the object is in the air determines the range or horizontal displacement of the projectile. Moving away from the general projectile motion concepts, let's look at some important concepts that are specific to things launched horizontally. First of all, when we say horizontal projectiles, we mean that they are launched exactly sideways. They have no upward or downward component to their initial motion. We must look at each dimension separately when we're analyzing this. And horizontally, the object is going to move with constant velocity, and that's what's shown here. This would be the path if we could turn gravity off and the object was just moving horizontally with constant velocity. Vertically, the object is going to move in free fall with uniform acceleration, and this is what the motion would look like if it was only falling vertically. And we can see, because it's uniform acceleration, the speed and distance traveled is picking up as time goes on. It's getting faster and faster. So we can take these two dimensions, the horizontal dimension and the vertical dimension motions, and when we combine them, we see that the object falls in a curved path. It's half of a parabola. And what's important about horizontal projectile motions, and you need to remember, is that the initial velocity is all horizontal. None of the initial velocity is vertical. So v sub I x is equal to the total velocity, and v sub I y is equal to 0. Once it's launched, the projectile will gain speed in the vertical dimension because the acceleration in the vertical dimension is negative 9.8 meters per second squared. However, the acceleration in the horizontal dimension is 0 because we're ignoring air resistance. So these four quantities here, the initial velocities horizontally and vertically, as well as the accelerations horizontally and vertically, are important to remember. Let's take a look and review freefall kinematics. Here are the basic characteristics that we just reviewed. An object can be dropped, thrown straight up in the air, or thrown straight down. If an object is dropped, its initial velocity is 0. If it's thrown straight up in the air, it's going to have an initial velocity in the positive direction. If it's thrown straight down, it's going to have an initial velocity in the negative direction. And this will be important when we're analyzing problems. We can then use the three kinematic equations to predict or describe the motion. Let's work through problem 1 on worksheet 1 to understand how we analyze vertical freefall motion. Here, a ball is thrown downward with an initial velocity of 20 meters per second. And it asks us to draw a motion map. So we start with an initial velocity, and of course it's going to gain speed because we have a constant acceleration due to gravity in the negative direction. Part B, what is the acceleration of the ball? Well, we know by ignoring air resistance, we only have gravity acting on the ball, and so the acceleration is 9.8 meters per second squared in the negative direction. Part C, calculate the displacement during the first 4 seconds. We're going to use equation 2 because we know the initial velocity, we know the elapsed time, and we know the acceleration. So we go ahead and plug in our values for the acceleration, the elapsed time, and the initial velocity, and we find out that the displacement is 158 meters in the negative direction. Part D, calculate the time required to reach 50 meters per second. We can use equation 1 for this because we know the initial velocity, we know the acceleration, and we know the final velocity. We go ahead and rearrange this equation to solve for delta t. We plug in our final and initial velocities, remembering to include the negative signs, and we wind up with 3.1 seconds required to reach 50 meters per second. Part E, calculate the time required to fall 300 meters. So we know the initial velocity, we know acceleration, and now we know vertical displacement. For this, we want to use equation number 2. However, initial velocity is not 0. Most of the time when we use equation 2 up until this point, the initial velocity was 0. The fact that it's not 0 makes this problem a little more complicated algebraically, and let's explore it. First, we want to plug in all our values. So we know the displacement vertically, we know the vertical acceleration, and we know the initial vertical velocity. We need to solve this for delta t, but this is challenging because we have delta t squared and delta t. What we need to do is use the quadratic formula. So we have to rearrange this equation to get it into the quadratic form. So we're going to add 300 meters to both sides, and that gives us 0 on the left-hand side of the equal sign. And on the right-hand side, we have a delta t squared term, we have a delta t term, and we have a term without delta t. If we think back to math class, this formula or this equation here fits the form of a quadratic equation. A times x squared plus b times x plus c. Notice delta t squared replaces x squared, delta t replaces x. Our a value is negative 4.9, the b coefficient is negative 20, and the c is 300. So armed with that, we can use our quadratic formula. We plug in negative 20 for our b value, we plug in negative 4.9 for our a value, and we plug in 300 for our c value. And when we crunch this in our calculator, we're given two mathematically correct answers, negative 10.1 seconds and 6.0 seconds. But of course, we don't have negative time in real life, so negative 10.1 seconds is not physically possible. The correct answer for this physical problem is 6.0 seconds. Now that we've reviewed how to analyze free fall problems, let's move on and look at horizontally launched projectiles. So we must use the kinematic equations to analyze each dimension separately. And so we've got a vertical dimension, which we'll use y to designate, and we have the horizontal dimension, which we'll use x to designate. Here is a step-by-step process for analyzing horizontally launched projectiles. First, list the motion quantities you know for the horizontal dimension. Second, list the motion quantities you know for the vertical dimension. Third, determine the amount of time the projectile is in the air. There are two ways to determine elapsed time, and the one you'll use is based on the information you're given in the problem. You'll analyze the vertical dimension to find delta t if you know the height, which is also the vertical displacement. You'll analyze the horizontal dimension if you're given the range or horizontal displacement in the problem. Lastly, you'll determine the vertical or horizontal distance, whichever one you weren't given. Let's take a look at a problem. A cannonball is launched horizontally from a cliff with an initial velocity of 40 meters per second. How far did it travel before it hit the ground, which was 30 meters below? So our delta y is negative 30 meters, and we're asked to find our delta x. First, we're going to list our known horizontal quantities. We know that the horizontal velocity is equal to the initial velocity, so that's 40 meters per second. And we know acceleration in the horizontal dimension is 0. Now we want to list our vertical quantities. We know since it was launched horizontally, the initial vertical velocity is 0. Because gravity is the only force acting on the projectile, we know acceleration is negative 9.8 meters per second squared. and the problem told us that the displacement was 30 meters in the negative direction. Now we want to find elapsed time, and since we were given the vertical displacement, we're going to use our vertical quantities in equation 2. So this is equation 2. Because the initial velocity is 0 in the vertical dimension, we can just cross out that term and not worry about it. When we rearrange it to solve for delta t, we get this form. We go ahead and plug in our displacement and accelerations, remembering to include the negative signs, and we find that it takes 2.47 seconds for the cannonball to reach the ground. We can use that information to find the range, the horizontal displacement, by using our horizontal quantities in equation 2. And so here we have equation 2. Horizontally, the acceleration is 0, so this first term with delta t squared goes to 0 and we can ignore it. We go ahead and plug in our initial velocity and our elapsed time, and we find out that the cannonball traveled 99 meters horizontally before it hit the ground. This wraps up what we wanted to learn about projectile motion in this podcast, so let's summarize what we've learned. First, projectile motion in general occurs when an object is moving vertically and horizontally at the same time. After the launch, gravity and drag are the only forces acting on the projectile. We're going to ignore drag forces because it makes the math too complicated. What's important to remember when analyzing projectile motion is we must analyze the dimensions separately. You cannot combine vertical information with horizontal information. They must be analyzed separately. In projectile motion, because we're ignoring drag, the horizontal motion is constant velocity, and the vertical motion is free fall because gravity is the only force acting on the projectile. And finally, when analyzing horizontally launched projectiles, we have to remember that all the initial velocity is in the horizontal dimension and none of the velocity is initially in the vertical dimension. I hope you found this podcast helpful and have a good day.